Hello, my name is Danica Globokar, and I'm the Senior Stormwater Program Manager at the City of Sammamish. This presentation goes over some key concepts to assist in policy making related to stormwater. A separate video will discuss application of these concepts to Sammamish. When rain falls on an undeveloped, forested site, some rain enters the ground or infiltrates. Some is captured by the tree canopy and then evaporates, and some runs off the site. We call this stormwater runoff. Several factors influence how much stormwater runs off a site. If the soil is very clay-rich, rain won't be able to soak into the soil or infiltrate, and more rain will instead leave as runoff. If there are few trees on a site to intercept rain, more rain will reach the ground and ultimately leave the site as runoff. Weather and climate also influence the amount of stormwater that leaves the site as runoff. Consider Puget Sound and think of soil as a sponge. In October, after a long, dry summer, soils are dry and water can infiltrate easily, just like a dry sponge. Very little stormwater leaves the site as runoff. Conversely, in February, after months and months of rain, the soil, our sponge, is now full of water and very little can continue to soak in. Thus, more stormwater leaves the site as runoff. Different size storms will change the runoff too. A larger storm will generally produce more stormwater runoff than smaller storms. The last main factor influencing runoff is human activity. Any change made to a site by humans will change the runoff from the site. Larger storms create more rain, and therefore more runoff, compared to smaller rain events. We talk about storms as inches of rain falling over a 24-hour period, and a likelihood of that happening. Climate scientists base the likelihood of happening on Washington's long-term rainfall data for specific geographic areas. For example, for central Sammamish, a storm event that drops 2 inches of rain in a 24-hour period has a probability of happening once every 2 years. We call this a 2-year storm. A storm dropping 3.3 inches of rain in a 24-hour period has a chance of happening once every 10 years and is called a 10-year storm. It's possible for multiple large rain events to occur in a single year. You can have 2 days in a row that each see 3.3 inches of rain, but the chances of that are pretty low, about 1 in 100 years. Development also changes the runoff from a site. When a site is developed, impervious surfaces, such as roofs, driveways, and roads, are constructed. Impervious surface prevents rain from soaking into the ground and infiltrating into site soils. Thus, as more and more impervious surface is added to a site, more stormwater will leave as runoff. These two schematics show how runoff increases when more impervious surface is added to a site. And remember, these are just rough approximations. On a forested site, about 10% of the volume of rain falling on the site will leave the site as stormwater runoff. 50% will go into the ground and infiltrate, and 40% will be used by trees or evaporated. In a high-density commercial area, where there can be over 75% impervious surface covering the site, 55% of the rain falling on the site leaves as runoff. Evaporation and infiltration are decreased in this setting. These represent only 2 end members of development conditions. As you'd imagine, suburban development, such as many of Sammamish's neighborhoods, would fall in the middle of these, producing more runoff than forested areas, but less runoff than high-density commercial areas. It can be challenging to think of stormwater in vague percentages, so I'll walk through an example with actual numbers and runoff volumes. Imagine you have a storm that drops 2 inches of rain over a 24-hour period. Remember, this is the 2-year storm event, and there's a 50% chance of this happening every year. Over a 1-acre area, that 2 inches of rain would generate 54,000 gallons of water, or rain, equal to about 2 semi-trucks full of water. For an undeveloped site, this would result in a 10-foot cargo van filled with water, leaving the site as runoff. For a suburban neighborhood with more impervious surface, Runoff would fill a charter bus. For high-density commercial areas, you would see a bit more than one semi-truck of water leaving the site as runoff. Where does that runoff go? A watershed, sometimes called a drainage basin, is an area of land where every drop of surface water, including stormwater runoff, ultimately drains to the same creek or stream. In Sammamish, we have 13 drainage basins, including the Zakoos subbasin and Thompson subbasin, which Ebright Creek drains. A forested, untouched watershed and the creek that drains it are in a dynamic equilibrium. The watershed and creek are roughly in balance, or equilibrium, but there is still some change in erosion that occurs naturally, which is why we call it a dynamic or changing equilibrium. Erosion occurs, but typically pretty slowly. However, when human activity like logging, farming, or building houses and roads occur in watersheds, and the watershed becomes more developed, more runoff goes into the watershed's creek or river. The watershed and creek thus fall out of balance because the same size storms happen with the same frequency but generate more runoff. This imbalance causes more erosion in creeks, more flooding because of higher volumes, and a decrease in summer base flow in creeks because infiltration isn't occurring as much. Creeks and lakes can also see decreased water quality from excess sediment in the water, pesticides, nutrients from agriculture and lawns, and temperature increases. So now that we've reviewed how runoff is generated and where it goes, we're going to pivot and discuss how we reduce the negative impacts of uncontrolled and unmanaged stormwater runoff. Fortunately, developers don't get a carte blanche to create impervious surfaces and generate uncontrolled amounts of stormwater runoff. They must build stormwater infrastructure to control the stormwater runoff. The city's adopted Surface Water Design Manual and Sammamish Addendum represent best science and provide strict guidance for stormwater management through construction of on-site stormwater controls, like stormwater ponds and vaults. Two of the key requirements for stormwater management and control are water quality treatment and flow control. Water quality treatment removes pollutants from stormwater before it leaves the site and enters our creeks, lakes, and wetlands. Flow control refers to regulating and controlling the rate and duration of stormwater flows leaving the site. I'll discuss water quality first. Certain surfaces, like roads, sports fields, and some roofs, contain pollutants. When rain falls on the site and hits those surfaces, it picks up those pollutants. An example of this is on our roads, where brake pads and tires deposit metal and rubber particulates on the road. When rain falls on roads, these particulates are washed off the road and enter the stormwater runoff. Without treatment, these pollutants eventually go into our surface water, like our creeks. The goal of water quality treatment is to reduce sediment, phosphorus, and other nutrients, and metals in the stormwater before the stormwater goes into our surface water. Those are our creeks. There are numerous ways to remove pollutants, and I've listed some here. The pictures you see are of a sand filter, which removes pollutants from the stormwater as water filters down through fine sand, and a vault containing dozens of cartridge filters, which filter stormwater through cartridges to remove pollutants. The second major requirement of stormwater management is providing flow control for the site's stormwater runoff. The peak flow matching requirement means that the rate of runoff leaving the developed site must not exceed the runoff rate from the pre-developed site. The runoff rates from the developed and pre-developed sites must match. Imagine a 2-year storm rains on a pre-developed site and runoff leaves the site at a rate of 5 gallons per minute, about half the capacity of a garden hose. After the site is developed, the maximum runoff rate from the site cannot exceed 5 gallons per minute. The extra stormwater generated must be kept on site and wait to be released at that 5 gallon per minute rate. Sites are also required to provide duration matching, which means that the length of time erosion-causing flows leave the developed site must match the duration from the pre-developed site. Development is not allowed to increase the duration of erosion-causing flows relative to the pre-developed site. Targets for these erosion-causing flows are set by modeling various sized storm events. Any proposed development must construct stormwater infrastructure to hold back the runoff and release it slowly so that the duration targets aren't exceeded. For more details and a more comprehensive technical discussion, Public Works will be sending a white paper following this meeting. In addition to peak and duration matching, we also require flow control best management practices, BMPs, sometimes called low impact development, LID BMPs. Flow control BMPs are stormwater infrastructure that mimic natural hydrologic processes, dispersing, infiltrating, or otherwise reducing the amount of stormwater runoff from a developed site. Flow control BMPs reduce runoff volumes by reducing impervious surfaces and maximizing infiltration and use of stormwater on site. Some examples of flow control BMPs are listed here on the slide. Flow control BMPs are a new requirement to the 2016 Surface Water Design Manual. Depending on the project size and type, sites must direct a certain percentage of their stormwater to flow control BMPs, therefore reducing the amount of stormwater leaving the site as runoff. The concept of volume matching has recently come up in discussions about stormwater. When a site is developed and more impervious surface added, obviously more stormwater runoff volume is generated. The Stormwater Manual does not regulate total volumes of stormwater runoff from a site, nor does it require volume matching because it's considered impractical by surface water professionals. Instead, runoff rates and durations are regulated in the form of peak flow and duration matching. Professionals consider peak flow and duration matching combined with flow control BMPs to sufficiently minimize the negative impacts of uncontrolled stormwater runoff. If a jurisdiction did require 100% volume matching for its stormwater runoff, what would that look like? It means getting rid of the extra volume of water on site through LID techniques or flow control BMP techniques. You could try to infiltrate the water, but on a site with poor soils, like much of upland Puget Sound and Sammamish, the water wouldn't infiltrate enough to get rid of all of the stormwater. You could try to have plants use it by planting more trees on site and intercepting the rain before it hits the ground, dispersing it over lawn, putting it in bioswales, or watering lawn in the summer. Ultimately, however, a developed site doesn't have the same tree canopy or ability to use rain as an entire forested site. The water could be used by humans for non-potable uses, such as for flushing toilets, but again, we wouldn't be able to use it fast enough. You could try something outside the realm of LID BMPs, such as boiling it or trucking the water off-site, but this is impractical. Ultimately, trying to match stormwater runoff volumes between a developed and forested site is generally not feasible, particularly if the site has clay-rich soils that don't allow for much infiltration. Building a bigger vault or pond cannot solve this problem. Once a site has removed trees and reduced the ability of soil to soak up rainwater, there are limited ways to dispose of extra stormwater at all, and very little chance of disposing 100% of it on site. In conclusion, this video discussed the science of stormwater runoff and stormwater controls, and how sites manage runoff and reduce the impacts of development on our creeks. This knowledge will help provide the technical background needed to discuss policy changes related to stormwater. The next video and discussion will focus on how this science is applied in Sammamish specifically, and policy changes we might consider.